Hi, so in this video we're going to look at the common base arrangement. So there's a common base amplifier here. I'm using a negative and positive supply rail. If you want to look at this with a single rail supply, so VCC and ground, or 0 volts, then you just bias the base using, say, a standard potential divider bias arrangement. So as you can see here, this is with this particular arrangement, this base emitter junction is going to be forward biased because of this negative voltage here. So if we draw this amplifier using a model, then we'll see something like these capacitors will become short circuit, or the power VCC and minus VEE would connect to 0 volts. So we could redraw this as follows. So we draw our model. So this is our beta IB. Looking into the emitter, we have a little RE. So this is our base, collector, and emitter. As you can see here, we are applying a voltage into the emitter here across an RE resistor. The RE resistor base is connected to ground. Input, we are putting the input across this RE, so this is our V in. I can say that that is our RC. Just put RC there. We also have this, I'm just going to put a dotted line for now, RL. So, what can we say about this circuit arrangement? Well, if we consider what the source sees looking in, so this, what we're going to do now is derive the Z in, then we can see that what V in actually sees is this RE, big RE resistor to 0, and also this little RE1 in parallel to 0. So we can say that that is RE in parallel with little RE. Now we know that little RE, RE1, is 26 millivolts divided by the quiescent IEQ. So we can say that that's going to be generally much smaller than our big RE. So this is why it's possible to have Z in to be very low impedance relative to this RE1 resistor. In terms of Z out, we can see that the load sees this RC resistor. So depending on the choice of RC, we can end up with our system having a very low input impedance proportional to this RE1 and a very high output impedance proportional to this RC, which makes it really good for matching super low impedance sources with high impedance loads. So audio RF type frequency applications. You'll notice though that the RL is going to end up in parallel with RC. So let's think about the current gain AI So we can say that obviously the current output here is this beta IB, this IC, we'll call it IC, divided by, and this current here, we've got, remember we've got this sort of beta current coming in here, so this is going to equate to the IE plus the IB, so that's going to be approximately 1. It's going to be just shy, it's going to be short because of this small base current, so yeah, 0.999 in value. So voltage gain, we can see that IC multiplied by IC is going to be our V out, so IC times RC, V out. Now the V in is determined by this IE here multiplied by RE. If we just neglect the IB for a moment, then we'll see that we will get IE times by this RE. So the ICs and the IEs are approximately equal, so they would cancel. So we end up with the RC over RE. However, we've also got this parallel combination of this RE1 in play here. So we can't neglect that in this setup. So this is in parallel with RE1, and we've already said that the Zin is approximately RE1, so we can say that the voltage gain is RC divided by RE1 approximately. Now, something that I mentioned previously, however, is that we have this RL resistor in parallel with RC. So when we're looking at this voltage gain, we have to be careful, and this is the voltage gain with no load attached. Okay, so no load. If we place a load onto this amplifier, then we will see, or you can specify that the voltage gain is going to be affected by this load because it goes into in parallel with it. So you need to be sort of careful if you're looking at matching the load that you're attaching to and your RC. Now obviously if the load is a high impedance load, then the voltage gain is going to tend towards the smaller RC resistor, which is pretty good. And obviously we've also seen that the input impedance is going to tend, if we keep the this quiescent current and 26 millivolt combination such that the little RE1 is going to be small, then we can get some quite good voltage gain, no current gain, but a good voltage gain from a low impedance source to a high impedance load, which is a pretty good use for this particular amplifier. So you could do this analysis in a number of ways. We could use a hybrid pi model. We'll get very similar results. And the other thing is we could just take Z-ins and Z-outs and put them in terms of the currents and the voltages. And again, you'll get similar output equations. So I hope that's been useful.